we're going to talk about rate now. And the rate of a chemical reaction is dependent a lot of times on the energy. Okay? So rate is how fast something is going to go per time. So the rate in your car, some of you I'm sure drive faster rates than others. Okay? But that's a rate, miles per hour. Here we're talking about how fast is the disappearance of a reactant over time. Okay? And that's what we define as our kinetics. So kinetics is the speed or the rate of a chemical reaction. And with this, there's a mathematical equation. You're not actually going to do the math. You just simply have to know how to set it up. That's it. You're not going to put anything in your calculator. You just have to identify whether it's put together correctly or not. All right. So this is the idea. A is broken down into B. So as A disappears, B is appearing, and these are going at the same rate. So they're related to each other. The rates of A and B are kind of the same. The disappearance of A is equal to the appearance of B, because this is a chemical reaction. Okay? Now if I had coefficients, which this doesn't apparently, but if I did, that would kind of change the speed of one or the other, because I need 2 of A maybe to make 1 of B. And so that would change the rate. The disappearance of A would be faster than the appearance of B, because A disappears 2 times faster than B appears. Okay? All right. So we can relate those two sides of the reaction that way. So a lot of times when we want to measure the rate of a reaction, we do it through color changes. So here you can see this color is disappearing because the reactant in here, as it's reacting, is going away. And as it goes away, the color is changing. It's getting less and less and less dark until it completely is gone. With what? Clorox? You could. Mm-hmm. So that, yeah, that could be a way. This one is probably bromine or something, or cobalt is a really nice color. So if you can couple your reaction with something that's colorful, then you can see the changes in the color over time. And you can measure using a spectral photometer. You can actually measure the concentration of this one versus the concentration of this one over time, and you can tell how much has disappeared. Okay? Yes, it does. Much better. Much nicer. Yeah, these don't show up as well. Okay, so for this chemical reaction to take place, oh, by the way, what type of reaction is this? Endothermic or exothermic? Exothermic. This is not it's not telling me the delta H here. It's telling me that I release 211 kilocalories of energy as a product. If they had written the delta H, they would write the delta H as delta H equals negative 211 kilocalories. They didn't tell me the delta H. They told me that I was in the reaction here. So it's exothermic. This is exothermic reaction. Energy is released. Okay? So be careful of that. All right? Okay, so here, for the reaction to occur, remember, I have to collide. And I have to collide with enough energy to do what? To break the bond. If I don't, I just bounce off. So I have to collide with enough energy to form a chemical reaction. Okay? That is called, that amount of energy that is required to break the bonds, it is called the activation energy. Okay? It is called the activation energy. The minimum amount of energy required to initiate that chemical reaction. That's my activation energy. So here is a diagram of what a chemical reaction energy diagram would look like. This right here, EA, that's the activation energy. So I start here, my energy starts here. I need that much energy for the bonds to break. Once they break, they will reform into something new, and they will release energy. So in this example, did I absorb more energy or did I release more energy? So what type of reaction is this? Exothermic. This is an exothermic reaction. Okay? What would a diagram of an endothermic reaction look like? That's right. So basically, the reverse of this, exothermic, I'm sorry, this is exothermic, this would be endothermic. Okay? Just simply the reverse. More energy required to break the bonds than is released. So this reaction now is endothermic, whereas the other one was exothermic. Now, what is the point of that with rate? Well, I have to break my bonds for my chemical reaction to carry forward. So the rate of the reaction is directly affected by those collisions. If those collisions aren't strong enough, what's going to happen to my rate? It's going to be very slow. But if I increase the number of collisions, what's going to happen to my rate? It's going to increase. It's going to get faster. If I increase the strength at which they're colliding, what happens to my rate? It also increases. How could I do that? How could I make them collide with more energy? Increase the temperature. So, temperature increases the rate of a reaction. What is another way I can increase those collisions? The number of collisions? The concentration. The higher the concentration, the more collisions that will be occurring. And statistically, the more collisions I have, the more opportunity there is for a chemical reaction to occur. So if I increase the concentration, I've increased the number of collisions, and I have increased the probability that a chemical reaction is going to go forward.
The energy goes up
with temperature. If I increase the temperature, more reactions. Concentration, more reactions. Okay? That rate has increased by temperature and concentration. Okay? The physical state, whether it's a liquid, a solid, or a gas, will also increase or decrease the rate of a reaction. Remember, it's about collisions. If I am in the solid state, am I going to easily be able to collide with something else? You're solid, you're stuck. I'm just sitting here. Well, if I push those two solids together at the surface, they might be able to react. But that's it. No other place. So the worst way you can carry out a chemical reaction is with solids. So let's put them in the gas phase. Now they're bouncing all over the place. They can collide with each other. Okay? That is good. But they're still far apart. So the number of collisions is still dependent on kind of the density of that gas. And gases are always kind of far apart from each other. The molecules are always in constant motion far apart from each other. Now I condense it. It's in the liquid phase. Now the molecules are actually touching. The number of collisions has increased by 1,000-fold because now the molecules are in close proximity to one another. So what's going to happen to the rate? It's going to go up. So what is the best physical state to carry out a chemical reaction? Liquid state. So if we can, we want to carry out a chemical reaction in liquid medium, because that's going to be the fastest rate. Okay. Now these two right here, structure of the reacting species and their orientation. Those are both very important to the rate. If I have a really gigantic molecule that's going to react with another really big gigantic molecule, and those two big things are trying to collide with each other in just the exact right way, they're going to have a hard time, because they're hitting all over the place, but not in just the right way. So, if I have, for example, nucleotides. Nucleotides are pretty big, okay, or amino acids. And I want to form a strand of DNA from these nucleotides, A, T, C, and G. If I put adenine, guanine, cytosine, and thymine in a test tube and let those molecules just roam around colliding with one another, I'm not going to come back the next day and have a strand of DNA. They're simply not going to react. They're just going to float around and do nothing, because they're too big and there's too much hindrance for those chemical reactions to hit in just the perfect way. However, in our bodies, if I want to replicate a cell, I want to undergo cellular regeneration. Yes? The DNA? Yeah, I've heard of that. Yeah, that's kind of cool. Use printers and things to do that, but there's other ways too. So in our cell, I want to replicate my DNA. How large is your genome? It's gigantic. It's gigantic. Every single chromosome has hundreds of thousands to millions of nucleotides on it. And your body has to replicate that perfectly. Because if it makes mistakes, what happens? Mutations. And, okay, sometimes that happens. Sometimes there's a mistake made. Okay? And you get a genetic disorder or cancer. Okay? But your body does a pretty good job. It does a pretty good job of it. How? Well, it uses a catalyst. What does a catalyst do? A catalyst reduces the activation energy. So by reducing the activation energy, I can cause the reaction to go forward with less energy. Oops, too far. Okay, so I have this much activation energy. I reduce it to this much. There's less energy required. How does it reduce activation energy? Oh. It stresses bonds sometimes. So if I want to cause a reaction at a certain place, I can stress the bonds there so they'll break easier. Or I can orient molecules, hold them in perfect positions so that chemical reactions will occur almost instantaneously, which is what happens when your body wants to replicate its DNA. That process happens very, very, very fast. So DNA polymerase has to grab the template strand, hold it in place, and bring a nucleotide to on top of that, hold it, bring the next one right next to it, and react those two. Then the next one right next to it, and react those two. But you see how fast it does it? It's tremendous. So this is the DNA replication complex where you have a leading and a lagging strand. This is the lagging strand that gets replicated over here in the leading one. Okay? But your bodies are amazing. People, these chemical enzymes, catalytic enzymes in your body, you have to, you eat your candy bar with 250,000 calories in it, and that your blood glucose level starts to rise. Well, what if it doesn't? What if you don't get that blood out of your system, into your cells? Very bad. Diabetes, you're going to go comatose, right? So your body has to release insulin to go to your DNA, say make GLUT4 protein, your body makes GLUT4 protein, which is a gigantic protein, like that. It takes it to the cell surface, and your body brings in the glucose, so you don't die. Okay, good idea. So that's what your body does. It uses catalyst to carry out all these chemical reactions. There you go. So how do we represent it mathematically? I just want to go over this. Mathematically, we say the rate is equal to the rate constant times the concentration of the reactant. Only the reactant, not the product, only the reactant. So here's the reactant, right? N2O5. These are the products. They are not in here in this equation, right? It is only the reactant. So rate equals the rate constant. That's a constant. You don't have to figure that thing out. It is given to you. Okay? You're actually not going to really be calculating any rate. So all you have to do is know how to write this correctly. That's it. How do you write the rate equation correctly? Rate equals the rate constant times the concentration of N2O5 raised to its order. Where do I get the order? You see how here A is raised to N? The rate equals the rate constant times the concentration of A, which is the reactant, raised to N. N is the order. Where do I find that number? It must be determined experimentally. You don't find it anywhere except in the question. They have to tell you what the order is. The reason I'm stressing that is because just after this we're going to talk about equilibrium constants. And the equilibrium constant, you find the order from the coefficient in the chemical equation. In rate, you do not. They tell you what it is. They tell you that A is second order. So if A is second order, then I write, in place of N there, I would say A squared. Okay? And I would say A squared. So here's some more examples. This is for this equation, A plus beta product. I would say rate equals K times the concentration of A times the concentration of B, because those are my my reactants. I don't include the products. Those are my reactants raised to their orders, N and M. And I don't know what those are unless they tell me. Unless they tell me A is second order and B is third order. Then I could write A squared, B cubed. But otherwise I would just leave them as N and M because I don't know what they are. Same thing here. Methane plus oxygen are the reactants, so those are the concentrations I use in my rate equation. K is times methane, concentration of methane, and oxygen, M. Okay? Now, let's see how it looks if they give you the orders. So here, the reactants are oxygen and ethanol. K times ethanol times oxygen. Now they told me that that's first order in ethanol, so I don't write anything because it's first order. It's just a 1, so I don't need to put anything. And third order in oxygen, so O cubed, oxygen cubed.
So the K, what do you mean to K at the beginning?
That's a constant. It's a constant that you don't have to discover anymore. They tell you what it is. If they're going to have you calculate it, which they won't, so in reality all you need to know is that the rate is equal to K times the concentration of ethanol times the concentration of oxygen cubed. Okay, that's how I write a rate expression. That is different than an equilibrium expression, because equilibrium expressions, okay, are written, let me show you, come on, in this way. The equilibrium, the KEQ, the equilibrium constant, equals the concentration of products over the concentration of the reactant. So this equation was written N2 plus H2 gives me NH3. And it was balanced. It was a balanced chemical equation. And that balanced chemical equation looks like this. N2 plus 3H2 gives me 2NH3. So I do the products over the reactants. Okay? Products over reactants. Concentration of the products over the concentration of the reactants. The main difference, though, I raise them to their orders, which are the coefficients. So this was N2 plus H2, 3H2, excuse me, produces 2NH3. So because this is coefficient of 2, that's why I square NH3. Because this is a coefficient of 3, that's why I cubed H2. This only has a coefficient of 1, so I don't put anything. I want to stress that because a lot of people make the mistake of using the coefficients on the rate equation. You don't. You only use the coefficients on the equilibrium equation. Okay, so what is equilibrium? So equilibrium is the process when the rate of your forward reaction and the rate of the reverse reaction have become exactly the same. Now what it doesn't mean is that you have equal concentrations on both sides of the reaction. That is something you want to think, but it's not true. Okay? It doesn't have anything to do with concentration, it just simply has to do with how fast your reaction is going one way versus the reverse direction. And once those are going the same speed, you have reached equilibrium. Okay, forward, reverse, forward, reverse, forward, reverse at the same speed. So it appears there are no changes at all. So the changes in the concentration going one way and the changes in the concentrations going the other way have stopped. There are no changes in concentrations at all. So the forward and reverse reactions are the same. Okay? That's what we mean by equilibrium. So an example of that would be this sugar. I dissolve it in water, it all dissolves. It's all gone. It hasn't reached equilibrium yet. So I take more sugar and I dissolve it in the water, and now not all of the sugar is dissolving. Because, or in other words, the concentration outside of the sugar, or outside of the water, and the concentration inside of the water are remaining constant. That is not because nothing is happening. It is still dissolving. But it is dissolving as fast as it is precipitating out. And so it appears that there are no changes in the amounts. Okay? So, appears nothing is happening. It appears like that, but that's incorrect. Because in fact it is still dissolving and it is precipitating out at the exact same rate. Okay, so the concentrations are not changing. That is simply going the same speed, in and out, in and out, in and out. Okay? Alright. Now, equilibrium is shown by the double arrow. The double arrow represents an equilibrium. Okay? That's how we always represent it. Okay. Okay, so this is how the forward reaction and the reverse reaction. So if I have this, the rate of the forward reaction would be Kf times the sugar concentration. The rate of the reverse reaction would be the Kr times the sugar. And if you put those two together, you divide them, you get an equilibrium constant, which is equal to the Kf over the Kr, which is equal to the sugar concentration over sugar aqueous over sugar solid. Okay? You don't have to really know that, because all you need to remember is that the rate constant, let me go back here, the rate constant is equal to the concentrations of the products over the concentration of the reactant. And I actually give you on your equation sheet this. I say that KEQ is equal to the concentration of C times the concentration of D raised to their coefficients, divided by the concentration of A divided by the concentration of B raised to their coefficients. I give you that general equation, which essentially would be plus in equilibrium with, okay? That's the equation, that's the general equation, and that's how I got that equation. Product divided by the reactant. So C raised to its coefficient, D raised to its coefficient, divided by A to its coefficient, and B to its coefficient. Okay? That's how I get there. That's the equilibrium expression. Okay? That's my equilibrium equation.
It comes there in the slide, that formula.
This is on the test material. So the reference material, this formula, yeah, it will. It comes right here. Okay? So I will give you this equation on the reference material. Okay? A plus B, you'll see D, that's my equilibrium expression. So if you can remember how to do that, products over reactants, then these will not be difficult. Now you might have to calculate something here with the KQ, but it's real simple. Because all they'll do simply, let me show you, right here, is they will give you the concentration. They will say at equilibrium HI equals 0.54 molar. H2 equals 1.72 molar, and I2 equals 1.72 molar. So if you set up your KEQ correctly, here's my equation. Product over reactant, H2, I2 over HI. H2 and I2 are not, there's no exponent because the coefficients are 1. HI has a coefficient of 2, so we have to square HI.
So if we have these two on the left, we have to put it like coefficient.
And you need to write it right here as the power of. And you need to square that. Okay? There's no coefficients here, so leave them blank. Okay? And then I simply say 1.72 times 1.72 divided by 0.54 squared, and my answer is 10.1. Okay? So if you set it up correctly, the math will not be hard. You'll be able to set it up. Okay? You just simply need to make sure that you're setting it up correctly. Use the coefficients as the orders when it's equilibrium. Don't use the coefficients as the orders when it's rate. Okay? That's the main difference. Okay, the Chatelet's principles. This has to do with equilibrium. So, when I'm at equilibrium, here I have the system at that equilibrium. It's all happy, content, and then I go and I stress it out. I'm good at that. That's my wife. So, I'm going to add stress to this equilibrium. How do I do that? Well, by increasing or decreasing something about it. So, for example, N2 If this system is at equilibrium and I add more N2, I increase the concentration of N2. What does it have to do to get back to equilibrium? I messed with it. I stressed it out. It's all stressed. It's not in equilibrium anymore because I increased the N2. What does it have to do? It's going to have to bring the concentration of the N2 down, right? So it's going to have to react N2 with H2 to produce more NH3. And then it'll start doing that until, once again, it reaches an equilibrium. And then it's not stressed anymore. Okay? So I have to decrease the concentration of N2. That's what I have to do.
Decrease.
It decreases I have to bring it back down, but this is how we say it. What they ask is, which way does the equilibrium shift? It shifts towards what?
Decreasing the one of those.
It does. It decreases both of those, and it shifts towards NH3, product. It shifts towards product. Or it shifts to the right. This is the right side. This is the left side. The equilibrium shifts to the right. Okay? So what would happen if I increase the concentration of NH3? It would shift towards the left. Whenever I increase something, it always shifts away from it. Increase, it goes away. It shifts away from it. So what do you think happens if I decrease something? Exactly. If I decrease H2, it shifts towards it. Or in other words, it shifts to the left or towards reactant. Okay? So this is kind of the language that you're going to have to recognize in these questions. Because they're going to ask, which way does it shift? To the right or to the left? Or towards reactant or towards product? Okay? So make sure you're understanding how that's working. So it shifts towards H2. Okay? What if I decrease N2? It shifts towards the not product, reactant, and that's the left. Okay? Decrease, and it always shifts towards it.
How do you know that it's decreasing?
Because they tell you.
How?
They say, if you decrease it N2, which way does it shift? If you increase NH3, which way does it shift? That's how they ask you. Okay? They ask you that way. Okay, so that's concentration. That's the effect of concentration. Now, temperature. Temperature works in the exact same way. Consider temperature as being a concentration of something. So look how they wrote the temperature in the reaction. They didn't say delta H negative or delta H positive. They simply put it in the reaction. Because for Le Chatelet's principles, putting it in the reaction helps you determine which way it goes. So, what type of reaction is this, by the way? Exothermic or endothermic? It's exothermic because heat energy is a product. So that means energy went out of, that means the delta H of this equals negative 22 kilocalories. So if they told you you have a reaction and the delta H is negative 22, then write it as a product, like they did. Because then you can determine what happens when I heat it up. If the temperature increases, which way does it shift? To the left, away from it, towards reactant, right? If I decrease the temperature, excuse me, which way does it shift? To the right, towards product. I don't think I did. You shift, once you increase the temperature, it shifts to the left towards reactant. You decrease the temperature, it shifts to the right towards product. Okay? You are? Okay. If you increase, it always goes away. Okay, so do you see how on the increase it went away from it?
Yes, decrease is away, but when it comes to the left and right part, then.
Okay, left and right is simply, if you're looking at it, it's either going to the left or to the right. No, not always, because what if I did this one? What if I increase H2?
Oh, so sometimes
it goes away. It depends on whether it's a reactant or a product, whether it's going left or right. Okay? But it's always going away if you increase. So if it is a product and I increase it, it's going towards the left. But if it's a reactant and I increase it, it goes towards the right, towards product. Okay? Alright, so when I decrease, it comes towards me. When I increase, it goes away from me. Okay, so what about this one? Endothermic, exothermic. Endothermic, it's a positive 39 kilocalories. They wrote that in the equation as a reactant. So if I increase the temperature, it shifts towards the right. If I decrease the temperature, it shifts towards the left. Okay? So that's the idea behind that. So concentration and temperature, alright, they're both kind of the same. But just if they gave you the delta H and it was a negative delta H, then write it as a product. If it's a positive delta H, write it as a reactant. Pressure. Now pressure, there's not just some simple up and away or down and towards. Okay? You got to think about this one. And they have to show you in the chemical reaction. So here I have this chemical reaction. I have N2 plus H2 yields NH3. They're all gases. With pressure, everything has to be a gas. It all has to be gas and pressure. So if I had a solid here, it wouldn't count for the pressure of the system. So I wouldn't worry about it. Okay, I would just worry about the things that are gases. Now, how many moles of gas do I have on the reactant side? More than that. I have 3 plus 1. I have 4 moles of gas. How many moles of how many moles of product do I have? 2. Okay. If I increase the pressure, which way does it shift? If I increase the pressure, it shifts towards the product, which is the right, so that the pressure will decrease. Now this system is in a container. I squeeze the container tighter and the pressure increases. Which way does this shift? Everything's in there already. I increase the pressure overall of everything. Which way does it shift? It shifts towards the side that will reduce the pressure. So if I have 4 moles over here, and I made more moles over here, that would increase the pressure. More. I want to shift this way so I can decrease the pressure, so I shift towards 2 moles. Okay? So I shift this way to decrease the pressure if I had increased it. If I had reduced the pressure, which way would it shift? It would shift towards the left. That's all it is. It depends exactly on how many moles are there. Whichever side has the least number of moles, it will shift that way to decrease pressure. It will shift towards the side with more moles to increase pressure. That's right.
Would it switch it sometimes? Like, put the product on the other side and the reaction. So it's always going to be like that.
Now they could write the reaction in the reverse direction, but then the NH3 would become the reactant. So if they wrote it NH3 produces N2 plus 3 H2. If I wrote it like that, then it's still, and now NH3 is the reactant. NH3 is the reactant now.
Because it has no moles.
No, just because I wrote it over on this side. Now this is the reactant instead of the product. Okay? So I would still describe it as shifting to the left or the right, shifting to the left for reactant or to the right for product. Okay. That's right. Okay, very important. This is a common question. How does a catalyst affect equilibrium? It doesn't. A catalyst has no effect on the equilibrium. It only affects the rate of reactions. Catalysts increase the rate of a reaction, but it does not affect the concentrations that they obtain when they reach equilibrium. Okay? So they don't affect that. Okay. Now there's one thing that I missed back here that I want to make sure we cover. Okay, and that's having to do with the equilibrium constant itself. Okay, so if your equilibrium constant is greater than 100, what does that mean? Well, KEQ equals to the products over the reactants. So if my number is 100, what do I have more of? Product or reactant? What is the bigger number? The top number, right? Product. So if my KEQ is over 100, that means I have a lot of product and less reactants. That's what it's telling me. What if my KEQ is smaller? So KEQ equals products over reactants equals 0.01. I have more reactant and just a little bit of product. So the concentrations are that I have more reactant than product. That's what that's telling me, the KQ. Okay? If they're about 1, what does that mean? Equal amounts of reactant and product. That's why it's 1. Okay? Okay, good.